I will be talking about epistemic logic, which is a modal logic of knowledge, where you have an operator that can express that agents know things about the world. And I'm going to present a new kind of model to give semantics to this logic, which is based on simplicial complexes. And it's not moving. Do we click? Yeah, okay, yeah, that works. Okay, so first, I will talk a bit about distributed computing, the kind of stuff that Dimitri was talking about this morning, because this is where we got the idea of using simplicial complexes from. So this is about solving distributed tasks, where you have several processes that are given input values, and then they are going to communicate in order to solve some tasks. So they exchange information about their inputs, and maybe they want to reach a consensus, or maybe they want to achieve something else. And there are many different computation models that you may want to consider, message passing ones, or maybe they communicate by writing and reading in a shared memory. And maybe they have more advanced communication primitives like test and set or other objects. So during this talk, I will not really assume any underlying model. I want to stay general and abstract. And I will just imagine that those processes are communicating through shared objects. And an object can be any of those things. At the end of the communication, the processes have to decide output values. And the task specification relates vectors of inputs with vectors of outputs. So this is a global specification of what all the processes achieve together. They are not competing, they are trying to solve the task together. And the task specification tells you for each pair of input vector and output vector whether you consider this correct or not. So here, this example would be correct if you want to specify consensus, where all the processes are trying to agree. And the goal here is to prove impossibility results, show that in some computational models, some task is impossible to solve. And to do that, many methods have been used in the literature. The very first and the most well-known result, called the FLP impossibility, is using a valency argument. What they do is they reason about the different executions of the system, and assuming that the task specification is satisfied, they will construct an infinite execution of the system, which is not something we want. We want the processes to terminate in a finite amount of time. Other slightly more abstract techniques have been used, one based on epistemic logic, where you try to reason about what the processes know about the input values of each other. And you try to find some logical obstruction showing that the task is not solvable. And combinatorial topology, which is what Dimitri was talking about this morning. In general, these methods based on combinatorial topology are very effective to prove impossibility results. There are some tasks like set agreement, where this is the only method that we know to prove the impossibility of solving a task. And the others are somewhat more intuitive, less abstract. They give you information about what the processes know and why you cannot solve the task. And so what I'm going to talk about is trying to reconcile those two approaches, the one based on epistemic logic and the one based on combinatorial topology. And this is based on a paper that we published in 2018 with the recent journal version with Eric Bobo and Sergio Rasbom. And so the idea is to create a direct link between epistemic logic and topology, and to use it to combine those two approaches to try to get the best of both of them. So let me explain in more detail what epistemic logic is about. So this is a modal logic where you have propositional logic, the conjunction and negation, and you have this operator ka phi, which is read a knows phi. And this A belongs to some finite set of agents that is fixed in advance. And so you can write formulas like A knows that B doesn't know that some formula is true. And in distributed computing, the agents are going to represent the processes, and the atomic propositions are facts about the worlds, maybe about the input values of the processes. And we will try to reason about what happens when they communicate, what kind of knowledge they can acquire. So let's do this little kind of puzzle of the two generals problem, where you have two generals, A and B, that are surrounding a fortress and they want to attack it. And they know for sure that if they attack simultaneously, they will prevail. But if only one of them attacks, then they will lose the battle. And so they have to coordinate, and to do that, they send messengers back and forth. But the messengers might be captured by the enemy guards, and in which case the message is not received. And so how will they manage to coordinate this attack? And here I will just assume that all the messages are always received. Maybe the guards are drunk from last night. And so let's see if they can coordinate for sure. Of course, A and B don't know that the guards are drunk. So maybe General A decides to attack at dawn, and she sends this message to B, which receives the message. So now both of them know that the attack has to happen at dawn. Is it sufficient in order to do the attack? Well, no, because A doesn't know that B knows. And so B has to send some kind of acknowledgement saying, I received your message, I agree to attack at dawn. So now B sends an acknowledgement. But it might be the case that this message is lost, in which case B, so now A knows that B knows, but B doesn't know that A knows that B knows. And so A has to send another acknowledgement to say, I received your acknowledgement. And you can imagine that I can keep doing that. And you will have a very long message saying, I received the message telling me that you received it. And you still cannot be sure that they both will attack. And what they need to be able to attack is called common knowledge. It's a kind of infinite formula saying that I know that you know that I know that you know, for any length of this formula. Okay, so now I will define the formal semantics of this logic. And I will do that using chromatic simplicial complexes. So you have a simplicial complex with vertices and simplexes, and I'm going to assign colors to the vertices. And here you might notice from the notation that my colors are going to be the agents, and so that every vertex has distinct colors. And moreover, I will consider first pure simplicial complexes, which means that all the maximal simplexes, here those three triangles, have the same dimension. So only triangles or maybe only edges, but you cannot mix dimensions. And now a pure simplicial model is given by such a pure chromatic simplicial complex, together with a valuation function that tells you at each vertex which atomic propositions are true or not about the particular agent. So let's look at this example where we have 4 cards, 1, 2, 3, 4, and 3 agents, A, B, C. We give 1 card to each agent, and the last remaining card is kept hidden. So one possible situation can be represented by this triangle, where each vertex represents an agent, here represented as a color, and the number inside the vertex is the card of this agent. Another possible situation is that one, where now agent A has received the card number 4. And here you can see that these 2 triangles are put together because from the point of view of agent B or agent C, those 2 possible worlds are indistinguishable because the only information they have is their own card. And so they cannot know whether they are in the left triangle or in the one on the right. And we can put together like this all the possible worlds. And if we do that, in the end, what we get is this triangulated torus. whose topology gives you some information about what the agents know about the world. And if you know about distributed computing, you might recognize the task that Dmitry was talking about this morning with assigning communication channels to the processes. And this is an instance of that. So now that we have a model, what we want to define is this validity relation, which says that some formula phi is true in some world X of the model C. And the worlds are going to be the facets, the maximal simplexes of this model. So we define that by induction on the formula, which is the usual definition of modal logics. Negation and conjunction are pretty trivial. And the interesting one is the case of knowledge. So you know some formula phi when this formula is true in every world Y, which is sharing an A-colored vertex with the current world. So let's picture it on some example. So here is my formula phi. It's A knows that B knows that the value of C is different from 1. And my world X is the one represented on the picture. So if I want to evaluate this formula in the world X, it's of the form KA something. So I need to evaluate the inner formula in every world that shares a purple colored vertex with this world X. And there are 3 of them, those 3. And now I need to check the formula KB, value of C different from 1, in those 3 vertices. So now I need to look at the worlds that are sharing a blue-colored vertex with those 3. And these are the ones. And so now I need, in all of them, I need the formula value of C different from 1 to be true. And this is the case. So as you can see, when you nest those knowledge operator, what happens is that you are going to explore this model. You are going to move from neighbor to neighbor and move inside your model. Okay, so what we proved about these simplicial models is that you have an equivalence of categories between simplicial models and Kripke models. The Kripke models are the ones that are usually used in epistemic logic, and they are based on graphs. They are one-dimensional structures. And here, this theorem tells you that from this graph, you can recover the equivalent simplicial complex. So you can extract this topological information from the graph. And this is interesting both for computer scientists and for epistemic logicians. For distributed computer scientists that are using those simplicial complexes a lot, this tells you that your model, your simplicial complex, is in fact a model for epistemic logic. So you can evaluate epistemic formulas on this model without doing anything new. You already have this model at hand, and you can reason about what the agents know. And from the point of view of epistemic logicians, this tells you that those Kripke models that you thought were just one-dimensional structures, actually they have this hidden topological information that you can extract. So as you can see, this equivalence holds with some conditions on both sides. The simplicial models must be pure and of dimension n, and the Kripke models must be proper and local, which I didn't define because these words will never appear again. So now I really want to take those simplicial models seriously and try to get away from those Kripke models and remove those extra conditions. So now we are not equivalent to Kripke models anymore, and let's look at what happens. So we want to generalize those simplicial models. And if we remove the condition that models have to be pure, what we get is this kind of model, like this picture on the right, which comes from distributed computing. It's a model of synchronous message passing with crashes. And typically, those models with crashes where some process might die during the execution will give you impure simplicial models. Because here you have this world, the triangle in the middle, W0, where all three processes are alive, but you also have the edges where some agent has died, some process has crashed. And so now there are only two agents in this world. And there are the three vertices where the other two agents have died. And so we studied these models in a recent paper. And first, we tried to find an equivalent class of Kripke models. We tried to kind of catch up from the side of Kripke models to see how they look like when they become equivalent. And I would argue this is not the most interesting part. This is kind of an intermediate step for the second one, which is to axiomatize the logic, to try to understand what this new logic that epistemic logicians have not considered before. What does it look like? What does it talk about? And so here I just recall the definition from before, because now this model C is impure, but we don't have to change anything in the definition. We just take the exact same satisfaction relation as before. And let's look at this tiny example with 4 worlds. In the world X1, there are 3 agents that are alive, and in the other 3, the agent A has died. So I will now stop using colors because it's a bit easier to read. And we have only one atomic proposition called P, and it's true exactly in this triangle X1. So let's look at some example formulas. I claim that in X1, agent A knows P. Well, yeah, of course, you look at agent A, there is only one possible world that shares this vertex A, and this is X1 where P is true. And on the contrary, for agent B, B doesn't know that the current world is X1. He thinks maybe we are actually in X2. And in X2, the formula P is false. So so agent B doesn't know P. Okay, another one in the world X4 on the right. Well, agent B knows that P is false, because from the point of view of agent B, we are either in X4 or in X3. And in both cases, P is false. And same for agent C. And now this is the interesting one. I claim that in world X2, the agent A knows P. But in world X2, there is no agent A. She doesn't even exist. Maybe she has crashed. Maybe she never was there from the beginning. So what does it mean to know something when you don't exist? Well, if you just look at the formal definition, there is this for all y, and there is no such y that shares an A-colored vertex. So this is vacuously true. And so here the agent A knows P, whatever that means. And last example, in world X1, I claim that agent B knows that agent A knows that P is true. So from the point of view of agent B, you have to check both the worlds X1 and X2. And here I checked both of them before. The first and the fourth line are X1 and X2. So, okay, that's a few examples. So what can you do with this semantics, this logic? First, you might want to talk about dead and alive agents. Currently, it's just some kind of intuitive notion that you see on the picture. But in fact, you can define it in the logic. Being dead means that you know false. As you saw in the example before, some agents can know something which is not true. And so, and being alive is the contrary of being dead. And you can check that this definition gives you what you expect, which is that the agent A is alive in some world. Now it's called W instead of X, but A is alive in world W when A belongs to the colors of W. So this is exactly the intuition we had, where we said an agent was dead because it doesn't belong to the edge or to the simplex. And so, there are some axioms which give some logic K before and which represents this thing. And you can prove some interesting formulas first. So dead agents, they know everything. So that's I've said that a few times. Alive agents know that they are alive. That's a nice thing to have maybe. And alive agents satisfy axiom T, which is called the axiom of truth. And this says that if you are alive and you know some formula phi, this has to be true. This formula phi is true. You cannot know something which is false when you are alive. So that's also a good property. Okay, and so now let's see another example of trying to push even further the notion of simplicial model. Until now, I was talking about simplicial complexes, pure or impure. What you can do, which is even more general, is the notion of simplicial set, where so now this is kind of, we have seen cubical sets a lot today, and now this is the same thing but with triangles instead of cubes. So you have a sequence of sets. S0 is a set of vertices, S1 a set of edges, S2 is a set of triangles, and you have these maps telling you that a triangle has 3 faces, which are edges, and a tetrahedron in S3 has 4 faces, which are triangles, and so on. And so with this notion, what you can do is this picture on the right, which is not a simplicial complex, but this is a simplicial set. And you can have 2 edges between the same pair of vertices. And so you can define simplicial models based on that, and you can use the same semantics as before. And the question is, what is the associated logic? What can we find actual situations where this is useful to model some stuff? And in distributed computing, from what I know, only simplicial complexes are ever used. So maybe we need to look at something else. And an idea I have is to look at cryptography, where you have these secret exchange protocols, where you have a secret key that you are going to break into small parts, and you distribute the little pieces of the key to several agents, so that if maybe 3 agents put their parts together, they can reconstruct the secret. And so here, on the picture on the right, you see the agents A and B individually, they cannot distinguish between these 2 worlds. But if they put their knowledge together, which is represented by these 2 edges AB, then these edges belong to only one world. So if they cooperate to share knowledge, then they manage to distinguish the 2 worlds. So this is something to explore. Okay, so I started the talk talking about distributed computing. Now let me explain in more details how that works. This idea of reconciling the 2 approaches, one based on topology and one on epistemic logic. So the approach of Herlihy that Dimitri talked about this morning, you have an input complex, and the task specification is modeled by some carrier map into an output complex. Then the execution of your protocol is another carrier map into a protocol complex. And you say that solving the tasks means that there exists a decision map from the protocol complex to the output complex. That kind of makes this diagram commute. And so the topological approach for impossibility results will claim that this decision map doesn't exist for a topological reason, because the protocol complex is connected and the output complex is not connected, so there cannot be a simplicial map. That kind of argument. And now what we do is we claim this decision map doesn't exist for a logical reason. So how can we find a logical obstruction to show that this map delta doesn't exist? So we use what we call the knowledge gain lemma, that tells you that whenever you have a morphism of simplicial model, which is this simplicial map delta that we had in the previous slide, and given any positive formula, here positive means that you are only allowed to talk about what the agents know and not what they do not know. So you can say phi can be, I know that the input values of the other processes are different from 0 or something like that. But you cannot say, I do not know that, or I know that he does not know that. So no negation, positive formula. Given a positive formula, if this is known in the output complex, then you can kind of pull back this in the protocol complex, and this knowledge that you have in the output has to be present already in the protocol complex. So starting from the input, you communicate to acquire knowledge, and then when you decide, you do not acquire any new knowledge. You have to know everything that you can in the protocol complex before deciding. And so that gives a kind of recipe to build these impossibility proofs. We assume that there is this map delta from the protocol complex to the output complex. And we have to choose a formula phi, which is witnessing that the task is not solvable. And we want this formula to be true in the output complex. So it describes the knowledge that is present in the output and which is not present somewhere in the protocol complex. So this is the amount of knowledge that you require in order to solve the task, but that you cannot achieve using this protocol. And so we use this ID for various tasks, for consensus and approximate agreement. For consensus, this formula phi is something about common knowledge of the inputs. If you remember the Byzantine, the two generals problem that I mentioned with the castle at the beginning, this was about common knowledge, and this was about agreement. And here for consensus, this is exactly the formal proof of this fact. And for approximate agreement, which is a weaker version of consensus, you want to have some kind of iterated knowledge. You want to say, I know that you know that I know some finite number of times. Then there is the task set agreement, which is kind of the stress test for these methods, because this is the task that I told you. We know topological methods to show impossibility, but we don't know any other kind of combinatorial method to prove the impossibility of that. And here we managed to give a proof, but in fact it's cheating a little bit. It's a proof that doesn't tell you anything interesting about the task. It's just the specification of the task. So here I think it's kind of a failure. But thankfully, on Friday you will have the talk by by Susumu Nishimura, who managed to apply this method for set agreements. And there is this published paper where he does that for one round. And on Friday we will have the full proof. So I'm excited to see it. And finally, another result we had is one based on a kind of toy task called equality negation. And here we have a kind of meta impossibility result. We showed that this technique for proving impossibility cannot work for this task. So there is no formula that can prove impossibility using these means. Okay, so now I will talk about some ideas of further research. And one is to try to enrich the logic, enrich the language of epistemic logic. Since there is this problem with equality negation, we have no formula that can prove impossibility results. Well, I say we need more formulas. We need more operators to express more kinds of knowledge in order to be able to prove impossibility results. And so one idea is distributed knowledge, which is a very important operator, which is the knowledge of a group of agents. I was mentioning that during the slide on simplicial sets, where individually the agents cannot distinguish the world, but as a group they can. And this is what distributed knowledge is about. So I think in the future, we should always include distributed knowledge to be able to make use of this high-dimensional topology. There is common distributed knowledge, which is the iterated version of distributed knowledge. And one very interesting thing about it is that it subsumes all the other operators. It subsumes common knowledge, distributed knowledge, the standard knowledge also. You just need this operator, and then you have everything. And maybe more exotic ideas would be to include some other topological operators whose semantics would be related directly to the topological properties of the model. Then it's not clear whether it talks about logic or whether this is just some logic of topological spaces. But yeah, we could try to invent some funky operators and see what the logic we get is. Another direction I would like to understand better is links between logic and topology. Can we have characterizations of topological properties via epistemic logic formulas? Here are some examples of how we could formulate those questions. Can we find a formula which is true exactly in the models that are pseudo-manifolds, for example, which is a combinatorial version of being a manifold that works for simplicial complexes? Can we find an axiomatization of the class of models that are collapsible? Well, I don't know. And maybe the easiest one is the third one, even though I don't have an answer yet. But what kind of formulas are preserved when you subdivide the complex? So subdivision preserves topology, but it doesn't preserve the logic, because when you subdivide, it takes more steps to go from one place to the other. So you need to iterate. I know that you know that I know. More times to be able to move into your complex. So it doesn't preserve everything, but does it preserve some kinds of formulas that are maybe always infinitary? Maybe they always look at the whole connected component. And finally, a third research direction is the link with directed topology. This is the notion of cube chain that Christophe was talking about in his talk this morning, where you look at the combinatorial notions of paths in a cube, and they represent executions of some distributed algorithm. And there is a simple bijection between the facets of the chromatic subdivision and those cube paths, which is maybe if you know about both of those things, this result is obvious, because they just describe the same distributed computing phenomena. What is a bit more complicated is to not have just a bijection, but recover the topology, recover how these facets are connected together. And this you can also do with the notion of partial cube chain, which I do not understand very well yet what they actually mean, but that's a first step to be able to maybe talk about epistemic logic on those cube chains. And here the main point of using directed topology is that we have this notion of direction of time that we could use to model temporal logic, where the processes learn things along time, whereas the simplicial complex model is static. It tells you what the processes know at one fixed point. And with directed topology, we have this extra notion of causality of time. And that's all I have. Thank you for listening.
So you mentioned about the sort of simplicial sense.
Mm-hmm.
Do you think that we can combine that with notion of dead and right processing?
Yes, of course. You could restrict to the pure simplicial sets, or you could have the full generality of simplicial sets. And I think it might be the easiest way to go just with the full thing and try to understand the general case, and then maybe specialize from there instead of trying to go from the bottom. But yeah, you can combine them. No.
This maybe a small question. So how is the logic exploitable?
So yeah, we currently we have only used it from the point of view of proving impossibility results. It would be nice to have some kind of specification language based on epistemic logic, saying that the point of solving the task would be a formula. Instead of saying you need to have this input-output relation, you could try to specify a task by saying you need to acquire this amount of knowledge. And then you could maybe, I don't know, have some verification algorithms trying you claim that your protocol achieves this level of knowledge. So you could maybe do some stuff to verify that it's the case. Yeah.
You can model check on directly on special complexes. It's interesting to check further when you have an algorithm. The protocol complex you get.
Yeah.
Okay, so thank you again.